So when we discuss concavity, we're going to be looking at the curvature of a function. Okay, so we're going to talk about, we're going to look at a couple of graphs and discuss what we mean by concavity, whether a function is concave up or concave down. But what we want to focus on right now is, what does the second derivative tell us? And the second derivative tells us about the concavity of the function. So that's the connection between concavity and the second derivative. Now you'll notice in our objectives here, we talk about using the second derivative test. So again, I made a distinction in the first derivative test about the difference in what the first derivative tells us and what the first derivative test tells us. And there's a common distinction to be made here. The second derivative is going to tell us whether a function's concave up or concave down. The second derivative test will tell us whether we have a local extrema or a local minimum or a local maximum. So these two can be misleading if you're not aware of exactly what it is we're doing. In this first video, we're only going to be discussing concavity and how to tell if a function is concave up or concave down. We'll come back in the next video and talk about using the second derivative test to determine local extrema. So there's a couple of slides that you might want to read through, but what I want to focus in is this one here. So we have these shapes. There's four shapes that we're looking at. And what I want to point out to you is the tangent line, these dashed red lines. Okay, so we might consider this to be tangent line 1, and this one here would be tangent line 2. So if I asked you to compare the slopes, right? So in this case, the slope of tangent line 2 is greater than the slope of tangent line 1. So basically what we're saying here is that f prime is increasing. In other words, the farther we go to the right, the steeper my tangent lines will get. So that's just another way of saying that f prime is increasing. Now let me do this right quick. If I'm going to write this out, and I want to make sure that we have a good understanding of what we're saying. If f prime is positive, f is increasing. Similarly, if f double prime is positive, f prime is increasing. Okay, so I think we can easily agree that, yeah, we've done problems like this. We know that is the case. Well, if I just make a slight adjustment to what's here and here, right? Now I can see the importance of what I'm talking about with concavity and how as we go towards the left, the f prime is increasing. So that's just to say, in this situation, if f prime is increasing, f double prime is positive. Okay? So if f prime is increasing, f double prime is positive. Now look at the one on the right, at graph B. In graph B, we're looking at an f prime that is decreasing. So again, we're talking about the slopes of these red dashed lines. And you can see that the slopes are decreasing, and eventually we'll have one that may even be horizontal. So if f prime is decreasing, another way to write that would be that f double prime is negative. Remember, if f is increasing, f double prime is positive. So the contrary, if f prime is decreasing, f double prime is negative. Okay. And then down here we have a couple more. In this case, we can see that our tangent line is negatively sloped. Now it's less negatively sloped. And if I continue, it will be even more less negatively sloped. I'm not sure if my grammar is correct there. But the point is that since these slopes, these negative slopes are getting closer to 0, that is another way of saying that f prime is increasing. And when f prime is increasing, f double prime is positive. Okay. Last one right here, I think we can see that this negative slope is not as steep as this one. And so this is just another situation where f double prime is negative, right? Because f prime is decreasing. Again, we can look at some of these slides. You can read these on your own, but what I want to do is point out to you what we have when we talk about an inflection point, okay? And it's really as simple as this. There is a change in concavity. An inflection point happens when there is a change in concavity. Take a look at this graph. If you look, we have a situation where this is concave down. We would call that concave down. And now our function is concave up. So we have concave down, concave up, and this change occurs at 0. So because the change occurs, the change in concavity occurs at 0, we would say there is an inflection point at x equals 0. You can read about that in these next few slides. And this looks very, very similar to the one that we just did. And in fact, it's pretty much the same problem. I'm taking a minute to read here. Let's see. Okay, so I missed something in this example. We're looking at, in this case, we're looking at f prime, and I almost went right by that. Okay, so we're talking in this problem, we're given the graph of f prime, and what I want you to notice is f prime keeps getting bigger and bigger and bigger, right? Okay, so because f prime keeps getting bigger and bigger and bigger, there's no change where the second derivative was negative and now the second derivative is positive. Let's go back and contrast these two graphs. So if we look right here, this is a graph of f of x, right? Let me see if I can erase. I think I drew right over it. It's hard to tell, but there's an f right here. So this is a graph of function f. And in this case, you'll notice that those tangent lines are getting less steep, okay? So our tangent lines are getting less steep. In other words, this is an area where the function's concave down, and if it's concave down, that means the second derivative is negative. Here, our function's concave up, and this is a situation where the second derivative is positive, okay? So now, back in our problem here, this doesn't happen in this problem. The values of the first derivative, right, f prime of x, those values are less than 0 right here. But remember, to discuss concavity, we're talking about the second derivative. And so those tangent line slopes are getting, right, the tangent line slopes are decreasing. Excuse me. I'm looking at, and I'm sorry, I swapped my paradigm for a minute. These slopes, these are tangent line slopes, they keep getting more positive. Okay, and that's what I mean is there's no change from a second derivative that is less than 0 to a second derivative that is positive. Let me give you, let me just draw what it would look like if there was a change in concavity. Okay. All right, so in this function that I'm going to draw in, we'll draw it in green. In this function, you can see that the tangent lines right here are getting less and less, these tangent lines are decreasing in value, okay? The tangent lines are decreasing in value. And now what are the tangent lines doing? Well, the tangent lines are increasing in value. And because there's a change from decreasing to increasing, we have a change in concavity. So f prime was positive, f double prime was positive. Now f double prime is negative. Okay, so what I've drawn here would be a situation where we would have a point of inflection. And what we have here, when looking, again, we're looking at the derivative, and that's what you always have to keep in the back of your mind, is that we're looking at f prime, not f double prime. Okay, so in this situation, if we're looking at f prime of x, we have no inflection points. We'll take a look at one more. Let's see, analyze the function, the following graph of f of x. Again, we're looking at function f, not like the last problem. Okay, so we're looking at function f in this case. And I think we can all see that right here, we have a very steep tangent line, and here we have a tangent line that is not so steep. And even right here, there's one that is even less steep. And I guess the more important of all of those, the most important is this one right here. There's a tangent line where it's 0. So these tangent lines on this in this case right here, f prime is decreasing. The slope of those tangent lines is decreasing. And when f prime is decreasing, that means f double prime is negative. Now on the other side, I think you can see those tangent lines, right, are going to start to get more and more negative. Okay, so they were decreasing, now they're getting more and more negative. That's still a situation where those tangent lines are decreasing. Okay, on this side, now we see that those negative tangent lines start to approach positive values. So when those tangent lines start to increase, when f prime starts to increase, that is when f double prime begins to be positive. Looking at the graphs can sometimes be a little more difficult. And one of the reasons why I'm doing all of the discussion right here is because I want to make sure you understand the difference in looking at f of x and looking at f prime of x. The most obvious thing to do is to look and see this was concave down, this one's concave up. And so where those changes in down and up happen, that is the point of inflection. And in this case, that point of inflection happens when x equals 0. Here's another good one to take a look at, just to hammer home. We're looking at f prime of x, okay? So that paradigm shift, right, that the way that I'm looking or what I'm looking at changes. And this one's very explicit. We're looking at the graph of f prime of x. Now, if I look, the value of the derivative right here is -1. And we can see that those derivative values are increasing. And so those derivative values continue to increase until we get to right here. Now the derivative values start to decrease. So we would say that there is a point of inflection at x equals 0. The reason we say that is because on this side, f double prime is positive, and over here we would say f double prime is negative. But there's one more occurrence, and it happens right here. And now we see that those derivative values start to increase again. So there's another situation where f double prime becomes positive. There are places where we have there are two changes, right? Two changes, one's at 0 and one is at 1. So let's take a look at what this says, right? By definition, the concavity is when f is concave down over an interval if f prime is increasing. And we see that f prime is increasing all the way up to 0. And then we see that f prime is decreasing from 0 to 1. Therefore, f is concave up over the remaining intervals. So this f is concave up for this interval, -infinity to 0. And f is concave up for 1 to infinity. Okay, concave up. And we would say that f is concave down. Concave down. between 0 and 1. So looking at the graph can be a little tricky if you're not aware of which one it is that you're looking at, f or f prime. There is a way that we can test for concavity by looking at the function very similarly to what we did when we were looking at those first derivative problems, okay? And we were looking to determine with the first derivative test. So let me get a blank piece of paper up right here because I want to use that to do this problem. We did one, this is going to look really, really similar to what we did in that first derivative test video, but let's take a look at this one, x to the third plus 2x plus 5, okay? So the question at hand here is, consider the function f of x, right? Over what intervals is f concave down? And the answer should be in interval notation. So because we're looking for when f is concave down, that is an indication to us that we want to know when is f double prime less than 0, or when is f double prime negative. Okay. Well, to figure this out, we're going to have to go in and figure out what the second derivative is. So the first derivative is 3x squared plus 2, and the second derivative is going to be f double prime of x equals 6x. So we want to know when is this concave down. We know that this function is going to have a domain of negative infinity to infinity. So what we're going to do is set this up with intervals, and our first interval is going to be negative infinity to 0, and our next interval is going to be 0 to positive infinity. All right. So I'm going to go in and find out what is the value of the second derivative at negative 1. And what's the value of the second derivative at positive 1? Okay, and I chose negative 1 and positive 1 because they were in the intervals that I've gotten, interval 1 and interval 2. I chose numbers that are inside those intervals. So I'm going to plug this into the second derivative. When I plug negative 1 in, I get a negative value. And when I plug positive 1, I get a positive value. So there are several things that we can say right here. First, we can say that f is concave down on the interval negative infinity to 0. And obviously, we could say that it's concave up for 0 to infinity. But what we really want to focus on is x equals 0 is a point of inflection. In other words, this is where our function would change from concave down to concave up at x equals 0. Now again, this chart is just organized a little bit differently than the way I did mine. You can do your chart however. I just want to make sure that you have the foundation to get the right answer. This is another problem very, very similar to what we did. The only difference is they're asking on what interval is this concave up. And you saw that the method we just employed would work both ways. So I'll let you go through the PowerPoint on this one. In the next video, we're going to talk about the second derivative test and how it's different than our test for concavity. So come back and join us in that video, and we'll take a look at a few problems there.